All right, so we're starting class a little bit late today because we watched two YouTube videos. They're both on Blackboard. The first one is about the weather, that gases expand and contract based on whether they are hot and cold, that evaporation causes cooling, that the capacity of the atmosphere to hold on to water is very, very different when it's warm than when it's cold, and that when you compress gases by pushing them into mountainsides, they lose their water, and we have convection currents that move from the equator to the pole, and they're divided into cells because of the Coriolis effect. It's a whole bunch of information in just 13 minutes. So that video is on YouTube, and then there's a quick one to follow about well, which of the gases in the atmosphere is responsible for trapping the heat, because we are concerned that the greenhouse effect is real, and we want to consider it. Okay. This is something that just popped up in social media just a couple of days ago, and it's an alarming trend of global temperature per year over the past 150 years. And from 1970s, industrial times, we're on a path. So one of the things that we talked about before we switched the camera on today was, just because that's the trend line, doesn't mean that we're heading there. There are a couple of other things that could happen, but yeah, clearly we don't want this trend to keep going. There's going to be a point at which an increase in the global temperature is going to impact our life, and certainly our quality of life. Okay. There's a couple of other things here. There's a couple of links. This data was pulled from, I found where they got the information from for that little diagram. Mm-hmm. It came from NASA. All of that information is public. It's all housed in here. They just redrew it. And this guy, this is a little infographic of, from 20,000 years before Christ up to the modern day, how our temperature has varied. So the midline here is what is compared to the temperatures between the 1960s and 1990s. So if we're on this side, we're colder than it was in the 1970s, and if we're on this side, it's warmer than it was in the 1970s. And it runs through all sorts of things like, oh, there was an ice age, and that New York and Boston were underneath at least a mile of ice. And yeah, the planet is covered in ice for a really long time, still a really long time. Humans start to form civilizations. We domesticate the dog. Things start to warm up. Okay, still 10,000, 9,000 years before Christ, and now it's flipped and we're warm. The trend line is now above temperature. So this is where people who have information are going to have a hard time having other people listen to that information. Because it used to be cold, and then it got warm all on its own. Why?
It was
Yeah.
meteor, right?
No, it was
Oh, just-
tens of thousands of years.
Oh, yeah. Oh, yeah.
It used to be super, super cold. Actually, not really that cold. It's only like 5 degrees colder than now as an average, but you know, localized temperatures will be impacted here. But enough that there was an ice age. And then the ice age went away. Was that our fault? Did we make the ice age go away? No. So now you're telling me that it's getting warm. But you told me in the 70s another ice age was coming. And now you're telling me it's getting warm. So did we cause the ice age? No. Did we cause the ice age to go away? No. It's getting hot now. You're telling me we did that as well? Okay, so here's where the little bit of resistance will be met. That nature does stuff on a long-term basis, which is why we started with weather, not climate. Weather. Weather is, hey, it's raining right now, and it's going to be raining for the next 3 days. Climate is, it's been in a warming trend for the past 100 years. Okay. But we were warm all the way through here. And this is now like 1,000 years, 2,000 years before Christ. And there are Roman documents. These are the one things that I remember, and I don't know quite where it would appear on this, but there are Roman documents that say, yeah, this is the amount of wine that the Britons produced this year. And this is how much we got, and maybe this is how much we taxed them. Wait a minute. I lived in England for many, many years. There's no wine industry in England. It's too cold. It's too cold to grow grapes in England. There's no wine industry. But there was in Roman times, because it was significantly warmer in England in Roman times than it is today. Did we cause it to get colder over those 2,000 years? No, probably the Earth did that. But are we causing it to get hotter right now? Yeah, probably. Yes. There is an elbow in this graph. They call it a hockey stick. There is an elbow in this graph that suggests this is not the same trend, the gradual up and down with an occasional blip here and there, but like an average. An average is an average. It's rainy one year, it's dry the next. But on average, it's about the same. You take a decade, it's about the same. You take a century, it's about the same. Right? As we continue to go, it cools down again a bit, and then there is this sharp turn right here, right in the 20th century. It actually was cold. One of the things that hasn't made it into the historical record, during the time of the First World War, Second World War, temperatures were actually cold. And then, we've got this. This is, there's nothing else on the thousands of years to suggest that this is normal. This seems to be man-made. So, we should probably do something about that. Probably. And then there's a couple of scenarios here that play out. Best case is we do something that impacts the temperature change and it levels off and nature takes over and pushes that number down. versus, we don't do anything. And those scenarios are troubling. Okay. All right, let's talk about where all this fits. Well, there was a word I learned. I've got to say this new word today. All right, so from the video, let's talk about weather versus climate. What's the difference?
Whether it's the day-to-day changes, or I mean, not even day-to-day, but like the predictive, like near future, like near changes.
Yesterday, today, tomorrow. It is on a short or near time frame. So I'm guessing that climate gets to be on a longer time frame. Let's talk about climate being on a long time frame. We just did that little infographic that showed how much, like 20,000 years or something like that. I can't remember exactly where I started. Is what happened 20,000 years ago relevant? At what point do we start saying, yeah, I don't care? I care about 1,000 years ago. I care about 100 years ago. I care about 50 years ago. Do I really care about 20,000 years ago?
I think it's important if you're looking at trends.
Yeah.
Right?
Meteorology is such a difficult science to predict. Models are great now. Computers and the advent of supercomputers, and now AI, has made it much, much more reliable. But there was a point, so I grew up where it rains all the time, but not predictably. So, you want to come out and have a barbecue this weekend? I don't know, because I don't know if 4 days from now whether it's going to be raining or not. Like, how can you not know? It's only 4 days away, because the weather was so incredibly changeable. You know it's going to rain, but you don't know whether it's going to rain at 2 o'clock or 1 a.m. or whatever. And computing has made that thing easier. But I remember in 1987, somebody called in to the BBC and said, you know, there's a hurricane coming. And the lead weatherman for the BBC, his name was Michael Fish, went on television and said, some idiot just called me up and said there's a hurricane coming. Listen, don't anybody panic. The chance of a hurricane hitting England is 0. We haven't had a hurricane in 1,000 years. Well, a hurricane blew through that night and killed people and knocked down thousands of trees and did untold damage. And the BBC, which is kind of a pseudo branch of the government, because you have to pay the government for the honor of receiving the BBC, didn't know. It was not predictable to them. It wasn't on their model. The 9 o'clock news didn't know that the hurricane was coming. How the world has completely changed. Now we can predict that. All right. Is this it? Is it just timeliness?
No, I mean, it's the, like, larger scale of it as well. Like, on, not just for, like, say, England, then it's for, like, the globe, right? For climate. Global, I guess.
Global or at least regional, right?
Yeah.
Because if people still do tune into the news to watch the weather forecast, but if I have to sit through 10 minutes of the weatherman telling me what the weather in Singapore and Dubai and Sydney is, when I want to know what the weather here is, then I'm not going to listen to that, because that's of no consequence to me. The weather in Sydney bears no relation to the weather here. And so the climate in Sydney does not bear too much of relationship to here. But something that impacts the global climate would impact us both. Yeah. So it's about reach and it's about time. And that should do it. Okay, let's see what we can pick up and remember from our little movie. Because there's a couple of really good points that were made there. The obvious thing is that the atmosphere is made out of gas. And where is the weather? The weather is in the sky. Yes, it can impact what's at ground level because of flooding and stuff, but the weather is up there. And that's because solids have their own three-dimensional mass and they are close packed and they don't, they're not impacted by changes in temperature and pressure very much. Liquids expand when you heat them and contract when you cool them, and they're fluid, they get to move around. But gases have big responses to changes in pressure and temperature. So this is where we're going to see the impact of changes in temperature and pressure. Okay. What can we remember? We'll pick something and we'll go from there.
Less pressure leads to, or is lower temperature? I was saying something about pressure and temperature.
So pressure and temperature are linked together. If I have a container, and that container contains a small number of gas particles, and I pressurize that. Now, there's a couple of ways to pressurize something, but one of the simple ways of pressurizing something is to restrict its volume. Because how gases relate pressure to us is that they bounce around inside the container. And every time the gas impacts something, it imparts a force. That force is the gas's pressure. If I compress the gas, then over the same period of time, I get more impacts, which means more pressure. And the way, so there's a volume pressure relationship here. So pressure is impacted that way. The other thing is, if I have a gas and that gas is compressed, so that I've got lots of gas particles inside a small volume, but I let the gas particles escape. As they escape and they put distance between each other, that pulls the energy away with them. And we see evaporation. Causes cooling. The high energy particles leave this part right here. And as they do, they take the energy with them. So there was a part in the video about, this is how a fridge works. You have a coil on the inside and a coil on the outside. And you circulate a compressible but evaporatable liquid through that coil. You just circulate it. But right between the outside coil and the inside coil, you put a constriction, and the gases pile up behind the constriction, and they get pressurized and they heat because you're forcing them into a space, and then they push themselves through the hole and leap out into open space, and they evaporate. So you liquefy the gases on one side and you evaporate them into a chamber on the other side, and that evaporation causes cooling and it pulls in heat from its environment. And on the back of the fridge is the coil that is hot, and it gives away its heat to the outside. So it pulls heat from inside the fridge and pushes it to the outside of the fridge. Okay. Where does the heat come from on the planet?
From the sun?
Heat on this planet comes from the sun. And remember that the sun gives us all branches of the electromagnetic spectrum. That we have the low energy infrared, visible, and then we have the high energy, the ionizing energies, the ultraviolet. Okay. Well, we get everything. We get the radio, the microwave, the infrared, the visible, the ultraviolet, the X-rays, and the gamma rays from the sun. But the part that makes it to the surface of the planet is largely here. Ultraviolet gets blocked by the ozone layer, so we don't get a meaningful percentage of ultraviolet at ground level, but the infrared gets through. Not all of it. A whole bunch of it gets reflected back. How does that happen?
From water? 80%.
This is our surface, and here's the light coming from the planet, from the sun. I've got ozone up here. the ozone is going to subtract out a whole bunch of UV. We don't worry about the X-rays and the gamma rays. We don't have a large amount of that. And microwave and radio is such a low energy wave that it doesn't really seem to be of very much consequence. But the visible light gets through. And the infrared makes it through. But if you just watch the shadows, it's daylight outside. That's the visible light coming through. Every now and then it goes dull. Oh, wait a minute, all the visible light isn't coming through anymore. Some of it is getting turned back. Some of it's getting absorbed. There are reflective things, some of which are on the surface. If you have an ice cap that's white and shiny, it will reflect the light back. And clouds contain sparkly objects, little water droplets that will sparkle and turn some of the light back. It turns out that quite a large percentage of sunlight is turned back. On page 167 it says, of the total incoming light, sunlight of all wavelengths that impinges upon the Earth, about 50% of the light is absorbed at its surface by water, lakes, ponds, seas, by soil and vegetables and buildings. Buildings get hot during the day. Stone gets hot during the day. A further 20% of incoming light is absorbed by droplets in the air in the form of clouds and by gases. This is where we're going to have to pick up when we're talking about greenhouse effect. The ultraviolet component is goes ahead and interacts with ozone, and the infrared interacts largely with carbon dioxide and water vapor. A small amount of sunlight is absorbed by soot and particulate matter. 30% of incoming sunlight is reflected back into space by ice and snow and sand and other reflective bodies. This is a new word. The reflected component of light is called albedo. Is that an environmental word that we've heard before? Is this a word you've heard before? Because I have not heard this before. Even though reading the book is the first time I've come across this. Okay. All right, so whole bunches of the light interacts with matter. Now, we've said that every component on the electromagnetic spectrum interacts with matter a different way. That ultraviolet interacts with matter by promoting electrons and ionizing stuff. That's why it's dangerous. Visible light interacts with the sensors in our eyes and we can see them. It's a lower energy, non-ionizing radiation, so we're not concerned about it. And then infrared does something really interesting. Infrared interacts with molecules, not atoms, molecules. The molecules have a particular shape. A molecule is just a collection of atoms. Here's a particular molecule that we'll see later on. This one's going to end up being methane. And infrared causes molecules to shake. Okay. Now, at the very, very simplest level, like middle school, beginning high school's general science class, there are two forms of energy that we can sub-classify all energy as. What are those two forms of energy?
Kinetic and potential.
Potential, that is energy associated with something's position in the universe, and kinetic, the energy associated with motion. All right, now, a molecule at room temperature has both of those things. The potential is trapped inside the chemical bonds. If we want to get it out, we have to react it with something and break those bonds and make new bonds. When I break bonds and make new bonds, I alter the energetic content of the molecule, and I will either release energy as either heat or work. Heat will involve a change in temperature. Work will involve moving an object from one place to another. As engineers, we're interested in moving objects from one place to another and doing work. As chemists, we're interested in the change in temperature. So we don't really see the work component very much. Okay? But the kinetic part is this. That bond gets to stretch. And if that bond is jiggling because the molecule is now in vibration, this is kinetic energy. And kinetic energy is the energy associated with heat, which is why infrared and heat are linked. Okay, the infrared component of sunlight is the component that we experience as heat. It's the warmth. Okay. In fact, physical chemist, you're not in this class, but what we did is we took several thermometers that were all glued to a piece of card, and we ran a rainbow that went red, orange, yellow, I'm going to need both thermometers, green, blue, indigo, violet. There you go. We ran a rainbow across the thermometers, the bulbs of the thermometers. And one of the thermometers read a higher number than the others. It read a higher value. Can you predict which one?
The orange.
Somewhere here. This one. This one. That one at the highest temperature. This is called the Herschel experiment, and there was a sunny, cold day a couple of weeks ago, and it was the perfect day to do this experiment. We took it outside on the the balcony out here in the shade, and then we pushed sunlight from a prism down into the shade, and we measured, oh look, these ones didn't change in temperature, and that one went up 1.5 degrees. How much was the
I
about?
wasn't here for this one.
Oh,
Yeah.
that's right, you weren't. I remember now. Yeah, I have the photographs, and you're.
I know which one would have gone up, but.
Yeah. So this one, there's red. This is the visible part of the spectrum. This is the infrared. Invisible part of the spectrum impacts the thermometer because that's the energy associated with heat. And we used alcohol thermometers. The red dye inside the molecule is an alcohol. It's just the red dye is dissolved in alcohol, and those alcohols start to shake when you hit them with infrared energy. And we proved.
Is that why like restaurants use red light if they're trying to warm food, or is
Yeah,
that nothing?
yeah. Those are infrared lamps. Yep. Yeah, they glow red because you want to see that they're on. I don't know if that's a side effect or it's just the economic reality of it. Yeah, those are infrared lamps. Heat lamps. You used to be able to get those for inside your bathroom, but we live in Texas and nobody needs that. But in other countries, they'll have like the regular white light that switches on inside your bathroom, and then another lamp that switches on red
We used
And
to
it-
always have them going, actually.
and heats the inside.
Those are really old.
Mm-hmm. I haven't seen one of them in a while, but I'm sure they still exist in other climates. Okay. So, infrared energy causes molecules to vibrate. The shaking is kinetic energy. This is heat. Therefore, the gases in the sky get hot. End of problem, end of chapter, close the book. No, it's slightly more complicated than that. There is a caveat, there is a rule. Infrared has a rule that it only I'm going to use the best wording that I can. Some stretches are what we call infrared active. The infrared is only active if the molecule, and I'm going to make this simple, because what we're really talking about is a dipole and a dipole moment, but I'm going to say center of mass, center of gravity, because it's easier to understand that way. The infrared is only active if the molecule changes its center of mass, all right, and in reality, in parentheses here, dipole moment. During the vibration. Okay. So, some things are easier to explain than others. And some things are harder to explain than others. That the two big culprits for the greenhouse gas effect, which is where we're going to trap infrared heat energy in the atmospheric gas, belong to a class of molecules that should not do this. Okay. I'm going to give you the very, very quick rundown of what's going on. Some molecules are polar. Polar molecules have a difference in electronegativity. Electronegativity being the ability to pull electrons. Atoms on the right-hand side of the periodic table: oxygen, fluorine, chlorine, nitrogen. These atoms are highly electronegative. They have an ability to pull electrons towards themselves. The full definition for electronegativity is the ability to pull electrons towards yourself within a covalent bond. The covalent bond being two electrons shared between two atoms. So if I pick something from the left-hand side of the periodic table and something from the right-hand side of the periodic table, there's a polarity there. And if there's a polarity, then moving it around, shaking the molecule, should change its dipole moment. Okay? So examples of polar molecules: water is polar because water is bent. If water was linear, oxygen is electronegative. It would be pulling electrons away from the hydrogens equally in both sides, from both sides. This water would be non-polar. But it doesn't look like that. It looks like this. And the oxygen pulls electrons away this way. So the oxygen has a buildup of electron density, and the hydrogens have a scarcity of electrons. And we have this little tiny separation of charge. Okay? Non-polar, there's no difference. So if I took an oxygen and I bonded it to another oxygen, like 21% of the atmosphere is, this molecule is not polar because both ends of this bond, this double bond system, are the same as each other. So nothing is pulling harder than the other. Nitrogen is the same thing. So this is 21% of the Earth's atmosphere. This is 78% of the Earth's atmosphere. These two molecules are non-polar and they are linear, which makes things simple, because if you are linear, you've really limited what you can do. You can go in and out. This is it. This is your stretch. So these molecular vibrations are going to exist in two forms: stretches and bends. But because this is a straight line, I can't bend around this bond. So there's only stretches. It's in and out. And the center of mass has not changed. These are not infrared active. They do not get warm when you push infrared energy into them. They cannot be the cause of the sky warming up. Here's where it gets a tiny bit complicated. Because the water vapor in the air will warm up. Water is has a very high heat capacity. It's one of the things that was in the video. So it absorbs a lot of heat over a prolonged amount of time, and it holds on to it for a long time, which is why the water at the beach, the temperature at the beach is always good, because the water takes forever to warm up and it takes forever to cool down. And so the temperature at the beach during the day is not hot, and the temperature in the beach at night is not cold. Here's where we're going to pick up the next time, because these are two non-polar molecules, but they're not linear. These are non-polar, but they are non-linear. This is carbon dioxide. Oh, when I say non-linear, and then I wrote the linear one, the polyatomic. I don't have three hands. The carbon is where my thumbs are, and the oxygens are where my fingers are. Carbon dioxide can stretch like this. When it does this, you do not change the center of mass. This is what we call a symmetrical stretch. This should be the dominant stretch. But it can also do this. Carbon stays in the middle, and this oxygen gets closer to it, and that one goes further away. And then this one comes in, and that one goes out. This is an asymmetric stretch, a pump action. This changes the center of mass of the molecule, as does this. This is a bend. This is a flex where this goes up and down. And these two, which should not be the dominant stretches, and we'll pull up the actual infrared data for methane and for carbon dioxide. Carbon dioxide doesn't have a lot of stretching in its spectrum. It just has this little band at 2200-ish. And it's the non-symmetrical stuff. Methane's more complicated. It's got a whole bunch of different things in there. Methane has this shape. It's tetrahedral. This is tetrahedral and non-polar. And this is linear. And we'll take a moment on Thursday to look at the modes of vibration. And then once we identify these as the culprits, then we'll go figure out where does it come from and what can we do to stop it.